Good afternoon, good morning, good evening to all of those who are here. It's my great pleasure to introduce Professor Jorg Schulze. He'll be talking about Bauhaus meets microelectronics. It is part 2 of the lecture. He already gave part 1. He's a
That's
full professor and chair of electronics devices at the Friedrich Alexander University at Erlangen-Nuremberg. He's a very experienced semiconductor physicist and engineer who has a long history of working in research, industry, and academia. He's also skilled in R&D development for semiconductor-based micro, nano, opto, power, and quantum electronics. Uh, he has been a pioneer in doing semiconductor education by bringing Bauhaus philosophy to microelectronics that aims to bring talented people, including women, into the field. He gave the first lecture a few months ago. This is the second part of the lecture. I urge you to go look at the previous lecture at the CRE website. With that, I will hand over the mic to Professor Schulze. Thank you very much, Jorg. It's all yours.
So thank you very much for the kind introduction and the nice opening of my talk. I will close now the window that you don't have these gray box in the upper right corner. The problem is now I don't see you guys anymore. I just can hear you. So if you have questions, feel free to interrupt me immediately, ask your question, but please do not raise electronically your hand. I will not see that.
Yeah, well, I'll take it.
Welcome to my second part of my lecture on the Bauhaus, which meets the microelectronics. And as Sab already mentioned, I gave already a couple of months ago part 1, where I more or less gave the motivation and the inspiration, or better to say, how I found the Bauhaus. And I gave a talk about my initial ideas to bring Bauhaus and the Bauhaus principles and philosophy into microelectronics education. And in the second part, Sab was asking me now to go please in greater detail to tell us or to tell you what we are finally doing and where do we meet Bauhaus in our education on microelectronics, what we developed now in Erlangen. So let me start with this little slide because, of course, the whole story more or less started in the year 2008, where I became a professor at the University of Stuttgart. What was more or less my first job as an academic teacher, asking the question, okay, what is good education? What we have to do to train our young people into for engineering and all that stuff. And of course, I collected during the very first years a lot of things what is not running good in modern academic education, especially in the Western world or especially in Germany, which I tried to formulate here with some statements. This is, of course, not fully complete, but just to give you a taste, a flavor, what problems I have seen as I started my job as an academic teacher. So, and you see it on the headline, the lecture is dead, long live the lecture. If there is a thing we permanently do in academic education is to give lectures, and what we permanently criticize, what is definitely not a good way to teach, is giving lectures, and then we discuss a lot of things and we continue to give lectures. And we formulated, okay, let's say the forms of teaching in universities are more or less outdated and we need new forms of teaching, mainly also to increase the students' own activity. And lecture is not a right way of doing that. Especially if you look to the academic education in Germany, we often have the problem that the practical relevance of the subject we teach at the university is more or less hidden behind missing competencies of students in applying the knowledge to new concepts. Often, that is what students told me. They feel a big distance between us teachers and the students, coming from the problem of a mass university, coming with the anonymity the students feel, and every student is more or less one of many. And also Sab already mentioned that one of the biggest problems in engineering we face is that in most fields of engineering, if you look to young talented women, the fraction of young women inside the study courses is way below 20%. And over the last years, we also faced the problem that the overall numbers of students want to go into an engineering subject is further decreasing. And we tried a lot of things during the last 20 years to increase the numbers, especially also to increase the numbers of young women. And to be very honest, we most of the time failed completely here. And still the big question is, okay, what we are doing wrong. And that is also a special problem we have in Germany, that in the past 20 years, we did a lot of things in the fragmentation of our study programs. 20 years ago, it was all, let's say, electrical engineering. And meanwhile, we have a bunch of special study programs on the bachelor and the master level, which are more or less all dealing with electrical engineering, but with very special subjects. And here we see that it's getting harder and harder and harder for the students to find a path through this diversity of our study programs. And especially for us as teachers here, a problem comes because the impact of us teachers is massively decreasing due to this fragmentation. Because in 15 years ago, I could tell my story why to study microelectronics. I addressed electronics engineers or electrical engineers, and 99% of the students sitting in front of me choose electrical engineering. So the story I told was fitting. Now I have a bunch of students more or less studying all electrical engineering, but the headline of their subject is medical technology or whatever, and then they permanently ask, okay, why I have to listen to this guy standing in front of us because he's more or less addressing electrical engineering. I'm not studying electrical engineering, and that is a big problem of this fragmentation. The impact of us teachers is decreasing, and I can tell now the next couple of hours more problems I found. This is maybe for the starting point to give you an impression why I started to look in greater detail, okay, what we should change in the education, especially in my subject of microelectronics in electrical engineering. And the very first question was, for me, we educate engineers. In German, der Ingenieur. And here it is interesting to ask, okay, what or where engineer or the ingenieur is finally coming from. And engineer is not coming, or the original word is not coming from the engine, it is coming from the Latin word ingenium. And this is what you also see here in the translation. The ingenium is the talented mind or the creative mind or the ingenious invention. So finally, if we educate engineers, means we educate or we want to bring out the creative mind. And then the question is, okay, what we have to do to bring out the creative mind. This is one of my first statement I made, okay, to reach then innovation or even disruption in electrical engineering. And this is why we are training our students in engineering. Engineering must be understood as a creative job. And to see, okay, what we are doing exactly at the moment, then later on you will understand what we have to change here to train our students in a creative way and to bring out the creative mind. For that, let's have a look how we do it at the moment. And here I show you a typical module structure of a typical engineering bachelor program we have at a German university. I don't translate the slide, so it's not important that you fully understand what's here named. It is the bachelor program of electrical engineering and information technology. And what you see here, okay, the students obviously learn within the very first 2 semesters basic courses on high math and experimental physics. Then in the third and the fourth semester, we obviously study some basic modules in electrical engineering. And then obviously we go into focus lines because then we just have focus line modules. So it is not further stated, okay, what focus modules here are behind. It is not important. We just check, is this running within 6 semesters? And then it's fine. And of course, and this you must keep in mind, we created these module structures just to check, is the study program we created, is this fitting into 6 semesters, yes or no? But we are using this module structure to stand in front of our students and to describe what they have to study. And just to give a feedback of one of my students on these module structure is what they say is, we have no clue what we study. And we also have no clue why we study that. The only thing what we know now from that program is we have to make it within the next 6 semesters or within the next 3 years. And very often then the students say, and if I fail, then I'm doomed. So that is what is more or less the entrance or the entry point in the study program for our students. And the question is, okay, whatever I study here, I have to do it in 6 semesters, but I don't know what, and I don't know why. And again, we have to bring out the creative mind. And then let's have a check what we do if we give lectures, if we give exercises and tutorials. What is the basic principles, learning principles we are following? And this is what I will show you in a minute, is more or less only learning by repetition. Just to give you this also on my classical lecture I give here in Erlangen at the university. So we go into the lecture, and here you see one of my slides I then present to my students to explain, in my case, the p-n junction, which is a basic microelectronic element we have to teach to the students, and to describe how to model it, how to describe it, and yeah, I describe what you can see here. And then we go into the exercise, where we more or less extend a little bit the knowledge, we repeat the knowledge from the lecture, and with the help of some exercise tasks, we more or less repeat, and we add some extra knowledge coming from calculations or coming from further explanations during the exercise. Then, especially in this lecture, we also have tutorials where, again, the students are getting tasks on similar problems they have to solve now by their own, which is, of course, supported by our scientific assistants, which are walking around and answering questions if the students have some. But more or less also here, but now by themselves, the students just repeat what they learned. And hopefully also here, they gain again a little bit more knowledge. And what is the end of the lecture program? At the end, we have always the exam. And then we formulate an exam task, which is more or less asking, okay, in this case here, please draw the model of a p-n junction. And what finally I want to see here is that more or less my students are going back to the slides I've shown in the lecture and drawing exactly the same picture here inside this diagram. And then they get full points, and then they get a mark, and then we say, excellent work, you learned a lot. So we just learn by repetition. If we are coming to concepts given by the design theory, where we had said, okay, we always have to divide into the concept space and into the knowledge space in the CK theory. If I now ask, okay, in which space I'm acting here as a teacher and where my students are permanently working, this is more or less just in the knowledge space. So finally, the exam is defining the space in the knowledge space, what knowledge the students should acquire during the lecture time. We start, of course, with the lecture giving a certain knowledge in the field. Then hopefully with the exercise we give, we expand the knowledge space of the students. With the help of the tutorials a little bit, we further expand that. And then, of course, we hope that by homework and by self-motivation, the students then also expand their knowledge by themselves so that they fit into the knowledge space we define by the exam, so that they successfully can go through the examination and get the final grading. But you see here, all this work is inside the knowledge space, which is good. But if you want to have a creative mind, which is able to use the knowledge for whatever conceptual work, we are never leaving the knowledge space and entering the concept work. The same, so the only operations we have is the case space to expand knowledge. Then very often our lectures are coming with lab courses. And here the lab courses we define as the practical part of our study program. But again, if you're looking again into the details, what we are doing here with the students, we do more or less exactly similar things like we do it in the lecture. For the preparation, we give the students some text knowledge. They have to read in advance. We also give tasks they have to solve in advance to prepare themselves for the lab course. And then they are coming to the lab course, and here they find predefined experiments and measurements, which are described by the text, and then they just now make the experiment described in the paper they have prepared a few days before by the textbook, or by the text we given to them and to the tasks. And then, of course, what is the result of the experimental work our students are doing? They collect a lot of data, measurement data. So then, of course, we train them a little bit on data analysis to use these numbers they have collected to show something. And this is what they have to final do after the lab course. They go into a documentation where they have a good representation of the data, give explanations in a written way. And this is what more or less we define as lab work, as practical work to support the teaching or to support the knowledge we gave into the lecture. But again, if we check again in which space do we operate, again, we see that we don't only enter the knowledge space, and we don't give any conceptual measures to use the knowledge in the concept space. So more or less the same picture here. We give a task for preparation and hope with a good preparation the students develop some knowledge in the field. Then, of course, with the predefined experiment and measurements, of course, we hope that the knowledge space is expanding. With the help of the data they collect in the data analysis, knowledge again is expanding. And with the documentation, hopefully the knowledge space, which you can gain here in this work, is maximum. But again, you see, again, just operations into the knowledge space. We do not enter into the concept space. So, and now is the interesting story behind. In the lab courses, we have our students in the lab, or to say it in the words of craftsman skill, at the workbench. But the work we are giving to them, or the task we are giving to them, have no freedom for own creation. They have no freedom to create something with the knowledge. And this is more or less what we are doing, very roughly said, in the classical academic education, at least here in Germany. But how it should look like. So the ideal world is, and I just give you this as a rough idea, only to go into further details how to do that, but it should be more or less that we have, let's say, a knowledge we give by the lectures or by the lab courses, which is always combined to a very dedicated problem in the concept space, where the knowledge is used to develop something, to build something, to create something. So, and of course, we should start to give the students concepts or conceptual work they can do with their knowledge, with the hope that so with the knowledge, they understand the concept and can start to play with the concept around. And then hopefully they see, okay, out of the concepts, alternative versions, C1 to C3, maybe reveal, which can be solved if the knowledge is a little bit expanded, or if the knowledge is way more expanded, that we understand more of the individual concepts. And then hopefully we should start a cascade that out of this knowledge, completely new knowledge for the student, is gained from the conceptual work, which again gives them, the students, the possibility to develop new concepts with this knowledge. And again, this is giving further knowledge, and so on and so on. So more or less the ideal world in education of engineers would be permanently to go from the knowledge to the concept space and back. And by working in the concept space to gain knowledge and to expand their own knowledge space. So this should be the ideal case. But if you look to our major two concepts, the lectures and the lab courses, we don't have this scenario, because we are only staying into the knowledge space, like I've shown you before. So To summarize that more or less, so what we are doing in a very nutshell, so we provide the knowledge for the development of concepts, but we rarely give guidance on how to navigate the concept space, to work with these concepts, to further develop the concepts. This is what we are not doing. And why we are not doing that? Because it is expensive in terms of time and resources, mainly of money reasons. And if you're asking why here, yeah, why it's so expensive in time and resources, yeah, because development of concepts in engineering involves trial and error. That means you need a lot to develop something new. That means you need a lot of time and resources. But we do not have time because they are all filled with lectures and with lab courses. So we learn through repetition. We do not learn, or our students do not learn by creation. And this more or less was the starting point in my personal thinking. Okay, what I have to change now as a teacher to work with my students and to go with them not only into the knowledge space, also into the concept space in my subject in microelectronics. And here the Bauhaus more or less was my inspiring part. And in the next minutes, I want to give you the roots of our Bauhaus initiative we developed. As I said, I already developed that in Erlangen, in Stuttgart, during my first professorship at the University of Stuttgart. And it was exactly in the year 2019 where we celebrated in Germany 100 years of Bauhaus. And to be honest, this was the very first time I really get into the Bauhaus, and I started to understand what creative school we have here, developed very creative ideas. Of course, not in my subject. So these guys were not microelectronics engineers. They were architects and they were craftsmen, but not engineers in that respect. And it catched me from the beginning that I was not looking on the Bauhaus due to art and due to architecture and due to their paintings. I was asking the question, okay, what they are doing with their students and how they train the students. And here I could see that more or less the Bauhaus principle they developed is true for all engineering subjects. You can adopt this to all engineering subjects and can get the same results out of it like the original Bauhaus guys have this 100 years ago. So this was more or less the starting point of my journey that I started to go into the Bauhaus principles. And this was actually my part one of this lecture that I gave you here a little bit more information on my own fascinating journey through the Bauhaus. I don't want to repeat, of course, my first lecture, but a little bit I need here. Of course, for the first time, I really started to read the manifesto for the Bauhaus education. I have seen for the first time the module structures they created for their students. You see it here on the right-hand side. And I was also reading the motivation texts, how these guys 100 years ago motivated their students to go into this subject. And I tried a translation of the German words. I don't want to read it by 100%. If you like, you can have the slides, or you can stop here the movie and can read it. So this is one of the starting texts to motivate the students to come to the Bauhaus and to start an education and a training program in architecture and in art. And this was very fascinating for me to see if I just change some of the words here inside this English text. This is highlighted here in English, what I have replaced by other words. You can keep more or less the whole text. And this is true, still true also for engineers and for craftsmen 100 years later. And you will, if you read that carefully, you will see it is fully independent if you are talking about microelectronics or whatever engineering subject or art and architecture. So this is always true. So what you learn here mainly from the Bauhaus, and the major principle of the Bauhaus was the workshop. And here, this is one statement I extracted from that work. So engineers, and that was my starting idea here behind in the new concept of my work. engineers, in my case, microelectronic engineers, must complete their theoretical education with hands-on experience in the workshop. So, and then of course, I also visited the original sites to look into the workshops of the Bauhaus. Here you see the original Bauhaus workshop from outside, the modern picture and an historical picture to look inside the metal workshop of the Bauhaus. And that was a second thing what absolutely fascinated me. The Bauhaus education attracted women a lot. So at the beginning, of course, I had no idea why especially women were so attracted by that. But it was a fact. The original Bauhaus was more or less overrun by young women wanted to study the program. And of course, that was also a driving force for me to go into further details, because here maybe that was my hope. I can find some measures what we have to change in modern engineering to attract young women for our work. And if you see what the old masters of the Bauhaus did, that was beyond architecture, that was theater, that was art, that was, of course, construction of furniture. So a lot of things behind one concept, and that was really bringing out creativity. This is one final statement I can make about the Bauhaus. If I look to the results the students could show later on, that was creativity by its finest. And then the question is, okay, what to do now and what to learn from the Bauhaus to bring that out of modern students studying microelectronics or engineering. So as I said, if we ask, engineers must complete their theoretical education with hands-on experience in the workshop, means we increase the students' practical abilities. The practical relevance then of our study comes through both theoretical and real practical education. The students must be closer to the masters, to us as teachers. So not in the lecture or in the lab course, we are there, the students are there. We must fill the gap. And here, and this is what the Bauhaus guys did, they closed the gap between the students and the masters by joint practical works. And Bauhaus was also a perfect example for thinking outside the box, using fixations. And this was also a statement, the Bauhaus was able to attract women. And more or less, that was finally my driving force to take what I learned from the Bauhaus, what I described a little bit more in greater detail in my first lecture, to bring that into my education with my people here in Erlangen. And this is what I want to show you within the next couple of minutes. So what are now the building blocks of our microelectronics initiative we have here in Erlangen? So how to adopt the Bauhaus principle to modern microelectronics. First of all, we completely changed the module structure I showed you before, and I adopted it to this scenario here, because first we were asking, okay, what finally our students learn, what we have to tell them if they come to our program. And if you ask, okay, what is the final goal in our education? It's all about the semiconductor device, the integrated semiconductor device we have on the chip. And this is given in the inner circle. At the moment, we have 4 areas of semiconductor devices, or 4 types of semiconductor devices in quantum, in MOS devices, in bipolar, and in photonics. And then, of course, the next question is, okay, what do you have to learn to understand the devices finally in these 4 quadrants of work? This is, you have to understand the materials, the semiconductor, the metal, and the insulator. And of course, you need a lot of concept knowledge to finally see how a semiconductor device is worked. And then, of course, you need knowledge about the fields of technology for what we are building the semiconductor devices, which is quantum technology, the CMOS technology, the photonic technology, and the bipolar technology. And of course, this is all wrapped by the basic studies in math and physics and general electronics and electrical engineering. And then we started also to tell in the beginning of the lectures our students a different story. Because if you look how many semiconductor devices are out there, we are meanwhile able to create, then I could fill, let's say, 10, 12 lectures just to talk about individual semiconductor devices. And to be honest, if I would do so, this would be completely boring. And that's why I decided to change my story a little bit and said, hey guys, it is very interesting to analyze all these semiconductor devices we create. And if you're doing that, then you will find out that we just have a bunch of central physical phenomena or central physical effects we can use mainly in the semiconductor for a semiconductor device. And what central physical effects and phenomena I'm talking about, you see here highlighted in the blue boxes. And we just have these, and you see here it's more or less 1, 2, 3, 6, 7 phenomena and effects where we can use in the semiconductor to create electronic devices. And if you then look what devices we created, you can collect them under the certain umbrella, for instance, quantum tunneling or the stimulated emission or the emitter effect. So here you will find all our devices. And this more or less gives you then also the fields of semiconductor technology where we are using those devices, so the photonics, the bipolar technology, the nanoelectronics, and the spin electronics. And this is more or less true for any physical semiconductor device you can create. So that is what you have to teach. We teach the central physical effects, and this is what then I use later on lectures, just to give, if you fully understand the effect, then you have open entry into the whole world of bipolar technology, just the effect and the whole world of technology. This is what we start to teach our students, that then of course we give dedicated examples for the devices using the emitter effect. But the target is just to train the emitter effect and said, okay, if you know that, then maybe you can later on create something completely new working on the emitter effect we haven't developed so far. And with this picture, I then can tell you, okay, if you are coming to my lectures, for instance, in the semiconductor engineering, I cover more or less the lower side of this slide. If you are coming to my quantum electronics cycle, I will teach you all the upper part of it. And the interesting fact is, whatever device you create, you need technology to fabricate those devices. This is good. We can use more or less similar technologies to create all these devices. And this is what we are covering in our semiconductor technology cycle. And this is always the starting point of our lectures, to bring the attention of our students to the effects and the phenomena, and to understand, we have to learn that first to understand the rest of the devices. And then, of course, we created a certain program, a very heavy program. You can learn a lot of semiconductor engineering if you're coming to Erlangen, which is following exactly this concept. But, and maybe I highlight this here a little bit here, it is very common that we name our lectures like I do it here: Semiconductor Engineering 1, Semiconductor Engineering 2, 3, 4, and so on. And of course, these numbers giving our students the idea, okay, maybe I should listen to Semiconductor Engineering 1 first before I go into Semiconductor Engineering 2. So it is just giving the students an order they should attend the lectures. We also changed that, even the fact that we are using the numbers and telling our students, and this is the second thing, hey, if you want to create an electron device in whatever area you're looking at, it is always the same semiconductor design process to create from the first idea the prototyping electron device. And to do that, you need a certain steps. We have identified in total 5 steps you have to undergo to come from a first idea of an electron device to the prototyping devices. And here, and this is how we then attach our lectures to this design process, there we said, okay, the modeling and simulation, this is what you learn in Semiconductor Engineering 3. The analysis of the manufacturability you learn in Semiconductor Technology 1. So we are not just giving by 1, 2, 3, just in order the student should attend the lectures to. We attach the lectures to this design process and tell the students, if you are coming to this lecture, then you are on this stage of the design process and you learn what you need to successfully go through that step in the design process. This is now also made for all of our lectures, that we permanently show on which part of the design process we are by attending the announced lecture. And this is also very important, that we changed our teaching philosophy, or better to say, we are using now all the same teaching philosophy in our lectures, which is based on the cultural historical psychology, mainly Vygotsky, developed in the 1920s. And this is highlighted under the title, The Stepwise Development of Mental Actions. And sorry for that picture. Allow me to explain you that step by step, that you understand what I want to show you here. If you want to create an electron device, then you have two things or three things you have to bring together. Let's start on the left lower corner. Here you see the cross-section, the schematic cross-section through an electron device with the individual semiconductor areas with different electronic properties, here highlighted in blue or in red. And of course, you have contacts to the dedicated areas where you can apply a voltage to, and then the current mainly is running through the device. So you always have the basic structure of the device. And of course, and this is what you see on the right lower side of the slide, if you apply now to the contacts a certain voltage, then a current is running through the electron device. So that means you have a characteristics of the device showing you how the current is flowing on the y-axis by applying a dedicated voltage to the device. And of course, the reason why we see exactly that characteristics, and this is represented in the top picture, is or can be explained mainly by the physics which is running inside the electron device, or better to say, this is what the electrons are doing, how they are traveling through the device, run by the physical laws in electrical engineering and semiconductor physics. And this threefold we want to use now to develop our teaching philosophy, so that we said, okay, we always want to train our students to think in the following way. So we start to study the old masters. Old masters means they have an idea of a device represented by the schematic drawing. Then, based on the physics which is running into the device, we can derive the output characteristics. So this is what they finally showed in the old papers of the old masters. You see exactly that. They presented the structure, they explained the physics, and then they showed what is the characteristics coming out. And then we tell our students, okay, the next step of the stepwise development you have to undergo is the following. If I give you the structure of the device, and if you give you the characteristics of the device, you must be able to tell me what is running, what's going on inside the device, what's going physically inside the device. That you, if we have made that, can go into the next steps. That if I give you the characteristics of the device, or the wanted characteristics of the device, you have a lot of physics knowledge, then you are able to deduct what structure you have to create, which is giving exactly this characteristics. That is then towards the art of engineering. And we are now switched our education in our lectures always to have these stepwise development. We start with the old masters through developing technical mastery to understand really what's going on, to create new things towards the art of engineering. This is how we now tuned our lectures to into that philosophy. So then, of course, we have meanwhile also created what we call the marketplace of ideas, because we can ask, okay, how many good and innovative ideas arise in the heads of our students during a lecture and then are dropped on leaving the lecture, by leaving the lecture hall. And here, and this is more or less the marketplace of ideas, that we ask our students If you have a great idea, bring it in front of us, coming out of the lectures, and then we discuss, okay, what we can do, what we must train to you that you are able to create the device or to fulfill your idea if we are giving you the right techniques. And so that means we, after discussing the idea, we will send them into the workshop, and then they get also a very dedicated workshop program to learn the tools and the machines, which is our clean room technology in microelectronics, that the students can or have the chance, if they have an idea, to go into the workshop and to realize the idea they have, and then to see, is it working, yes or no. And this is now, and we do it the whole line of academic education, that we said, okay, starting from the bachelor students, we send them in the workshop over the master students into the PhD students. And of course, very often here in the program, all of our students have very often a PhD student or the professor by itself on his side as supervisors. But, and this is what we took from the Bauhaus, one of the Bauhaus principle was that every student has two masters. Not only the academic master, always the craftsman, always the technician on its side. And this is what we add to our practical work, to the workshop concept of our work, that if a student is entering our workshop with an idea, or we give the idea and the student wants to realize, that always we have two supervisors for the students, one on the academic side and one of the technical side on the craftsman side. And of course, if it develops, then of course, higher level supervisors are then the supervisors of the higher leveled students. So, and meanwhile, we started with this, so we can say we already have the first generation of Bauhaus students in Erlangen. And just to give you an idea, so with that, we could teach students to do things more or less what is almost possible. So one of my female students really did the almost impossible. What she did is, by using our lithography machine, which is not able to have this resolution, but finally with some tricks she played and she learned, she could create a pattern with a 500 nanometer resolution on the surface, what is almost impossible with the technology we gave her in her hand, but finally she did it. And other example we taught basic principles here, for instance, in technology to deposit oxides. And meanwhile, he is doing his own experiments completely by himself in the clean room, in the workshop, on those oxides now, trying to find out something new he's interested in. He's just playing around with that. And the third example is from design to build. So meanwhile, we have students showing up with a chip design they have in mind. And meanwhile, we created a bachelor thesis on his own idea and gave him the technology that he's now tries to create his own chip based on the chip design he created. And the fascinating thing, if you're just open the workshop for the students, they are creative by itself by themselves, and this is what we have to push in our education. And if you look in my back, I'm at the moment sitting in my hotel room because every year I go with my students in the summer school in South Tyrol. So at the moment I'm here with my PhD students. So we of course add also very special programs to the education. Here we are in South Tyrol, in northern Italy, in the Alps, which gives a very special format where we work together with our students in the seminar styles in the mountains. And of course, 50% of our time, we are then also going into the mountains, continuing our discussion on what we learned or what we discussed in the seminar. So this also gives a further push to the creativity of our students. And this is what we are meanwhile doing every year in September. And this is at the moment, I'm here in the Ferienakademie with my PhD students, and this is what we also changed in the PhD level education, that we are forcing now our PhD levels always to work with the thesis slides, where they learn to extract questions, thesis, they must answer if they want to create something new within their PhD program. And the students learn by themselves. They just have a problem, which questions I have to raise, which thesis I have to raise to cut the given problem into smaller pieces, solve them individually, and to bring them all again together to have the final solution of this. So by this special approach, we also, meanwhile, for a couple of years, we are doing this now. We get more and more success in the creativity, how the students approaching their own PhD work they want to undergo. And this is now brand new. This is what we started last year, more or less. So far, I just discussed what we did to bring more or less the academic world into the world of the vocational training, more or less. So to combine the academic work and the vocational training world. But now the question is, and this is also interesting, so I've shown you now students into the workshop. The opposite question is, can we bring the technicians of the workshop back into the lecture? So because we have now 3 to 4 apprentices per year in microtechnology and IT and accounting in our institute, and of course they just undergo the classical vocational training. And we are asking now the question, okay, the students are now in the lab, in the workshop together with the apprentices. So maybe now we also should bring our apprentices back into the academic world, into the lecture hall. And this is what we are doing now. So, and the interesting fact is, we also have seen this in this clarity for the first time, that the track of academic education, the vocational education, is completely parallel. So that means you have the workshop students on the bachelor, master, and PhD level with now the 2 supervisors. But if you look to the vocational program, for every level, you have it on the vocational side. And this is how we now parallelize the program of the vocational and the educational program, so that we also give now 2 masters to the vocational training program, and 1 also from the academic side to support also the vocational education and the theoretical level. And we also invite our students to come with our academic students into the lecture hall to attend some lectures which are beneficial for their own vocational education. So because, so we made a lot of progress in the past month and year. And this is now right in time, because we are having new frontiers. We are looking at in Germany, and now especially in our microelectronics Bauhaus initiatives. If you now look to the projected demand on semiconductor and microtechnology professionals within the next 10 years, we are talking about several thousands of engineers and professionals which are able to work in the field of microelectronics. And one big question is, okay, how to get all these people and how to train them. And I think we are now pretty much at the point to give a concept, which could be a concept then also for all Germany, to train the students on the academic and on the vocational side for the needs of our industry within the next decades. And of course, we have our own ELISA community, and if you are interested, you are invited to join us here. We have a nice community where also our friends from Paris, and of course also our Indian friends, are highly invited to join here, where we are coming together. Here are the guys talking about the Bauhaus for new ways in education and management. So you are of course invited to join us here if you like. And yeah, to finish with a short outlook, if I look now to the timeline, it started more or less in the year 2019 with our first Bauhaus initiative in Stuttgart and our first marketplace of ideas. In 2021, I moved to Erlangen. So the Stuttgart Bauhaus went into the Microelectronic Bauhaus of Erlangen. And we are adopting now, and that was new, the vocational training together with the academic training. We made our first steps here. We are now on the stage, or we started last year, in scaling the concept to go to bigger numbers, and not only to a handful of students, to a lot of students. Hopefully that we have a good concept for the future, which can be scaled up to numbers to meet the industrial needs. This is what we are starting right now. And hopefully in 2025, we will see the next step of our development here in our microelectronics Bauhaus. And this was my last slide. And let me check my time. I thank you very much for your attention.
You're doing very well. You did excellent timing. I'm going to ask you a quick question because I have to leave. What I would like to do with you, which we can discuss in Paris, is your evolution and scaling process, both in terms of the problem and the institutional and social space you have created. You are aware of my PSI theory. I want to characterize what you have done using that PSI theory to show you have used CK. Now at another meta level, we want to look at how you build such institutions or Bauhaus institutions and write about it together with you guys. That is my wish, and I will stop there. It has been a wonderful lecture. I really enjoyed every bit of it. And Professor Shyam Sundar, who's there, and Sudhir, we have been talking about transforming engineering education in India. It's a hard problem, as you know very well, to see how we can take ideas from you and the process from you, document it, and show how a transformation can take place. With that, I will stop and thank you very, very much. And I might leave in 5 minutes. I have another call.
Thank you. I'm looking forward to.
Yeah.
Thank you, Jorg. Lots of good ideas that unfolding through the presentation. In fact, the first slide which you have shown in terms of the current state of students, right, which I think most of the points will relate to an Indian context as well, except one point, which is the number of students joining engineering. Actually, it is much higher here. There is demand far exceeds the supply. So other than that, rest of the points are equally valid in an Indian context. And also how you portrayed the limitations of the current theory and practice, which is largely restricted to the knowledge space. But one of the things is when you want to reorganize like this, do you see a need for reorganizing the labs physically, right? Because right now the lab structure and the research lab structure may be organized in a certain manner, which may not promote collaboration. So is that a constraint do you see in the way you have done it?
Not at all. We don't have to create new lab courses or new labs. What I want to stress is that we hinder our students to go into a creative phase of their own development. So they are so bound from us or by us, giving a text, read that, sit in front of this experiment, do exactly this, measure this, now draw the following line and interpret that and give an explanation. And of course, our students are following strictly that. Instead of saying, okay, you have to learn in the course by yourself how, let's say, to measure a diet and how the IV characteristics of a diet is looking like. You find everything inside the lab, find out what you have to do and do it. Yeah. So that is, I don't think we have to change the labs physically, yeah, or the installations. We have to treat our students differently just by pushing them to say, I will tell you anything. You have there the workshop, go inside and find it out. And this is what the Bauhaus masters really did. They gave lectures and explain why they are doing things, what they are doing. And then they had a big workshop with all tools, with all machinery, what is necessary. And then they said, go inside and find out, do something. They said, make your art. And of course, then if you said, okay, I want to make paintings as an art, then they could go into the workshop, found a canvas, and could make the painting. And this is what is natural for an artist, but we as engineers don't do that. So to come to the idea to say to the students, go into the workshop, find out something and make your art. This is not the words we are using, but I think this is what we should use in the discussion with our students, to give them an idea that our engineering is an art, and that we send them into the workshop to do their art, whatever their art is in engineering. And this is my observation. If you start to do this with young people, they have brilliant ideas. They just continue to work by themselves. And this is so fascinating to see, because we believe, okay, if we send our students in the workshop, then they're standing there and have no clue what to do. Then, and this is what I learned, we fully underestimate the young people. Just give them the opportunity. They go into it and they make their art. And this is what we have to learn as engineers, to tell our students, make the art.
Yes. A related question is this apprenticeship model, does it work in an engineering context, especially that level of attention? Is it possible to build in an engineering education model?
This is, so the apprenticeship program I spoke about is our major apprenticeship program running for 3 years. So a dedicated program with school time in school, and of course a lot in the lab, where you learn more or less on the shop floor level. You learn the profession. Yeah, it's not an academic education, but you learn from a craftsman perspective. You learn to do it, to do the technology. And this is a 3 years program. And after that, and you get also a certificate. You know, we are Germans. We always need certificates to be qualified. And this is running since decades in Germany, these apprenticeship programs we have. But at the moment, this is fully disconnected from the academic world. And I have now, so this is what my fortune is. In my own institute, I have both. I have the academic side and I have the apprenticeship side. And here the idea is, hey, look, we can perfectly match that together. So this is my hope, that we can elevate the level of education on the technical side by bringing academic students to it, and we can level higher the level of education of our academic students by bringing the technical side together. And here it's fruitful for both sides, and they can level up in parallel. And here the idea is just bring it together.
Thank you. Any other questions?
I think I'm going to leave. You guys go ahead. Thanks.
Sure.
Thanks, Jorg. I'll talk to you later.
Talk to you later. Thank you, sir. Bye-bye.
May I ask a question?
Sure.
Okay, this is Shyam Sundar. Professor Schulze, thank you so much for your excellent remarks and talks, and your remarks about craft and science aspects of engineering have been something that Sub and I have been talking about for last few years. And there's a issue that comes up in India. In India, the craft and science aspects of engineering have become separated in hands of people from different social classes. And that distance of social class of people who acquire craft skills and scientific knowledge makes it quite difficult, challenging to integrate the two. I assume that social separation between the two is not such a problem in Germany. Germany. Yeah. But what can be done in a society like India, where people, the social separation is an additional challenge of bringing this Bauhaus concept of craft and science together.
Maybe so. Even the fact that I traveled a lot through your country, of course, I'm not really an expert about Indian problems. I'm just a visitor, seeing things, but it would be very hard for me really to give you an advice. But maybe you can see or learn something from that, what I've seen here in Germany. In Germany, we made the following mistake. Over the last 20, 30 years, we continuously said Germany has too less amount of academics. We need more academics, more academics, more academics. So we have now the situation that in Germany we have roughly 25,000 bachelor and master programs. I have no clue what you can all study here. And we fully run out of people of crafts. So the traditional crafts jobs are now running empty because they do not find people. And if we ask, okay, where the young people are, then they are all at the high school, at the colleges and at the universities. In Germany, we have the problem that no one, so everyone is running on the colleges and on the universities and not doing crafts. And the interesting fact is that if I discuss with young people, they feel the wish also to work with their hands. And so my initiative more or less is fulfilling or is giving them a satisfaction to that, because in my education they learn a lot of theory, but they can also do a lot with their hands. And here I learned that people now also learn that it's very value that you're not having anything inside your brain, that you are also able to do something with your hands. And this levels up the way of viewing on jobs you do with your hands. And maybe this could be one approach, to tell that people which are working with their hands have a very value contribution to the society itself. And if you now give the chance, and this is what I'm trying now, to those who mainly work with their hands, also to give a certain access to the academic education on the university side, then you bring them together and you level both up. And maybe that is a little bit more difficult in India than in Germany, especially. So fortunately, we don't have the problem with the caste system I'm pretty much sure still have in your country, even the fact that officially it is it was shut down. So of course that brings more problems with it, but I think that could be one approach.
Thank you.
Thank you. Anyone else in the audience has any question? Okay, so thank you, Jorg, for taking time and speaking to us and providing a next level detail in the experiment or the implementation that you are doing. We wish you all the best in your initiative and look forward to engaging going forward. So thank you again. Thank you for your time.
Thank you very much. And thank you for the invitation. It was a pleasure talking to you. Goodbye.
Sure. Thank you.
Bye-bye.